Hello everyone and welcome to our operations management video tutorial about linear programming. In this video, we will answer 5 theoretical questions and further show an actual example on how to apply it on Excel. Let's start. The first question is, what is the ultimate goal of management decisions? The ultimate goal of management decisions is to make the most effective use of the company's scarce resources, such as machinery, labor, money, time, and raw materials, in order to meet customers' requirements and targets. Managers must consistently and continuously make resource allocation decisions to identify the best or optimal choice, making production planning one of the most important tasks in production management. The main challenge of production planning, therefore, is finding an optimal solution while taking a wide variety of conditions into account. One method that helps to achieve this goal is linear programming, a quantitative tool used to obtain maximizing or minimizing solutions to problems that involve constraints due to scarcity of resources. These objectives and constraints of linear programming problems are expressed in terms of linear equations or inequalities. With linear programming, product mix problems can be solved. In many manufacturing firms, 2 or more products are usually produced using limited resources. The profit that the firm seeks to maximize is based on the profit contribution per unit of each product. By solving the product mix problem using linear programming, the firm would like to determine how many units of each product it should produce to maximize overall profits given its limited resources. There are numerous examples of linear programming applications to such problems, including identification of the best combination of workers for a specific job and developing optimal production schedules. When solving linear programming problems, the following basic assumptions apply. Firstly, the numbers used in the objective functions and constraints are known with certainty and do not change over the period concerned. Additionally, proportionality exists in the objective function and constraints. Lastly, all activities equal the sum of the individual activities, and the solutions do not necessarily have to be whole numbers. The following question is about how to solve a linear programming problem graphically. To solve a linear programming problem graphically, we need a two-dimensional graph which can be used to identify the optimal solution to the model. To find an optimal solution to a linear programming problem, we must first identify a set of feasible solutions. The first step in doing so is to plot each of the problem's constraints on a graph. We can plot the decision variable on the horizontal axis of the graph and the other variable on the vertical axis. In all problems, we are interested in satisfying all constraints at the same time. The feasible region is the overlapping area of all constraints. An optimal solution to the linear programming problem always occurs at a corner point of the feasible region. To find the optimal solution, we need to evaluate the objective function value at every corner point in the graph. Following, we will talk about some limitations and special features of linear programming. The first limitation takes place in some cases when redundant constraints are drawn. These constraints are the ones that do not affect the feasible region in any way. This means that other constraints in the model are more restrictive and thus negate the need to even consider the redundant constraints. This can happen, for example, when a constraint can be reduced by an entire number. The second limitation is about infeasibility. This happens when no single solution satisfies any linear programming problem's constraints. Thus, no feasible solution region exists. Such a situation might occur, for example, if the problem has been formulated with conflicting constraints. The third limitation takes place when we arrive to an unbounded solution. This happens when a linear programming problem may or may not have a finite solution, as the objective function grows beyond bounds. One special feature about linear programming is the fact that more than one optimal solution exists. This happens when the level profit runs parallel to a constraint and the two lines have the same slope. The presence of more than one optimal solution allows management greater flexibility in deciding which solution to select.
Hey guys, now that Lydia has given you a theoretical introduction to linear programming, we would like to show you a quick example which implements the before mentioned ideas into Excel. So in our example, we have the car manufacturer Volkswagen, which produces two types of cars, the Golf and the Beetle. And our goal throughout this example will be to maximize our monthly profit. And to do so, we will have to determine the amount of Beetles and Golfs which will maximize our profit during this period. Here we have the objective function, which depicts our profit as a mathematical function. And we can see that the Golf creates a profit of 6,000 per unit and the Beetle produces a profit of 5,000 per unit. But this is not all. The production capacities of Volkswagen are limited, and those limits are embodied by those 4 constraints that we have set up for you right here. And the first one depicts the total amount of labor hours we have available for assembling the cars, which amounts to 600,000 hours in total, and which then has to be split up in a profitable way between the 2 models. The same logic also applies for the second constraint, which depicts the limited labor hours the car company has available for painting the cars. The third constraint emerges out of the requirement of our marketing department, which tells us that we must in total produce at least 16,000 cars. And here it doesn't matter if Beetle or Golf is produced, it just matters if one car is produced or not. And the last constraint is crucial for linear programming, and it depicts the non-negativity constraint, which means that the 2 decision variables, G and B, cannot be negative. So to illustrate this example graphically, we have already set up a small graph for you. Here you can see again the constraints just illustrated. So the black constraint depicts a assembly hour constraint, the red one depicts a painting hour constraint, and the blue one accounts for the minimum requirements set by our marketing department. And the area that you see right here, marked in yellow, is the so-called feasible region. And the feasible region depicts all different output combinations of the 2 car models that at the same time adhere to the given constraints shown before. And as Lidia mentioned before in the theory part of the video, we can also nicely see a corner point here in our example, which is the intersection between the assembly hour and the painting hour constraint. This corner point should later then turn out to be our optimal and profit maximizing product mix of the 2 car models. And now that we explain it graphically, Greg will show you how to solve this product mix problem with the Excel solver.
In order to calculate the corner point using Excel, we use the following table. We can calculate the profit of the company by using the sum product function. In this case, we must multiply the number of units produced by the markup per car, namely 6,000 for the Golf and 5,000 for the Beetle. Of course, the outcome of the calculation is 0, since we did not deduce the number of units that have to be produced. We must then set the formula of these 3 cells. For the 3 left-hand side constraint cells, we want to express the previously mentioned constraints into Excel format. As you can see here, we do the sum product for the 2 cells using the number of units, so the yellow cells, with regard to the assembly hours and the painting hours. In the last cell, we simply add up the total unit produced, which are expressed in the yellow cells. We will now use the solver by going to Data and then click on Solver. In the solver, the set objective corresponds to the profit of Volkswagen. The changing variable cells represent the number of units of car produced. Then we also plug our variables and finally select the solving method simplex all P. Furthermore, we must select the sensitivity report option, which we will explore in more details later. Once the result is displayed, we can now see the optimal profit as well as the corresponding number of cars produced and also the final value of the constraints. Now, to get back to the sensitivity report, the variable cells table is composed of a few columns. The final value in both tables corresponds to the amount of cars and the total amount of labor hours, which maximizes profit in our example. The reduced cost we see in the upper table predicts the additional profit we make if one more unit must be produced. However, as we already exhausted all our resources, we are not able to increase the units in a profit maximizing way, which is why the reduced costs are zero. The objective coefficient here are just the ones we saw in the objective function before. And the allowable increase and decrease tell us how much we should increase our output without having to reconfigure the Excel solver. Now, we will be explaining the lower tables which represent the constraint. The final value represents the value of the constraint functions if we use the profit maximizing decisions variables, which in this case, the maximizing value possible of the constraint. The shadow price represents the additional profit generated by an additional unit of the different capacities. Allowable increase and decrease follow the same logic as in the previous table. That's it, guys. Thank you very much.